Have you ever really stopped to think about it? How do the words we type into a screen actually make a computer do something? It can feel like magic, but today we're going to peek behind the curtain.
So yeah, how do our words become the computer's actions? It's this incredible translation process, and it all comes down to a really cool piece of science, the science of compilers. So let's get into it.
Okay, so let's start with this idea of a secret translation, because that's really what's happening. Every single time you hit run, your code starts this amazing journey. And the guide on that journey? That's the compiler.
So what is a compiler? Well, at its core, it's a translator. That's it. It's a special program that takes one language, say the Python or Java that we write, and translates it into another language.
I like to think of it as a bridge. On one side of the river, you have us, writing in what we call high-level languages. They're designed for humans to read and understand. And on the other side, that's the machine, which only understands these super basic, low-level instructions. The compiler, it's the bridge that lets us cross from our world to the machine's world.
And this isn't new stuff, by the way. The ideas we're exploring today, they're built on decades of incredible work all laid out in these foundational computer science texts. This is really the heart of how we build things with code, and it's a pretty elegant story when you break it all down.
All right, so if our code is going on a journey, where's the first stop? Well, the first thing a compiler has to do is turn our code into words. It starts by breaking everything down into the smallest possible meaningful pieces.
Let's take a line of code you've probably written 100 times, something super simple like this. To you and me, this looks totally obvious, but to a compiler, it's a puzzle that it needs to solve, piece by piece.
Because right now, to the compiler, this isn't a sentence. It's not even words yet. It's just a long string of individual characters. So what's the very first thing it has to do? It's got to figure out where the words even are. Okay, so this first step has a fancy name, lexical analysis. All it really means is that the compiler scans along and groups the characters into what we call tokens. So it sees RESULT and goes, aha, that's an identifier, a variable name. It sees the equal sign and knows, okay, that's an assignment operator. It just keeps doing this for the whole line until that meaningless string of characters becomes a nice, orderly sequence of meaningful words.
All right, so the compiler has its words, but just like in English, a pile of words isn't a sentence, right? You need grammar. So the next step is to figure out how these words actually fit together. It needs to build a blueprint.
This part is called parsing, or syntax analysis, and honestly, it's a lot like diagramming a sentence back in English class. The compiler is basically checking our grammar. It makes sure the tokens are in an order that makes sense, according to the language's rules. If we wrote something like 5 equals value, for instance, the compiler would throw an error, because that's just not grammatically correct in most languages.
And what it builds is this. This is a syntax tree. It's that blueprint we were talking about, a perfect picture of our code structure. Look at how it works. The main action, the equal sign, is at the very top, like the root of the tree. To the left, you've got what we're assigning to, the result. And to the right, you have the whole expression that we're calculating. At this point, the compiler finally, truly understands what we were trying to do.
Now, once it has this blueprint, the compiler can get really clever. There's a phase called optimization, where it looks at this tree and asks, is there a better, faster, or smaller way to do this? It's kind of like a good editor trimming the fat from a sentence to make it punchier. The meaning stays the same, but the result is just better.
Okay, so that's the basic journey. But you might be thinking, this is cool, but why does it matter? I'm probably never going to build my own compiler. And that's a totally fair question.
Well, there's a quote from one of those classic textbooks that I think just nails it. The point is, the ideas you learn from how a compiler works, they aren't just for building compilers. They are some of the most powerful problem-solving tools you'll ever encounter in software.
Seriously, think about it. The techniques for scanning text and building these trees, they're used everywhere. They're inside the tools you use for text processing, the programs that automatically find bugs in your code, in cybersecurity, even in designing computer chips. This stuff is absolutely fundamental.
So learning this stuff isn't just about passing a class. It's about learning a new way to think. It teaches you how to take a big, messy problem, break it down into small, logical pieces, and then build a really elegant and efficient solution. It's the science of how we build things with code from the ground up.
So next time you sit down and write a line of code, maybe just take a second and think about the quiet, incredible journey it's about to go on. Because when you understand the compiler, you're really understanding that beautiful, hidden logic, that amazing bridge between your ideas and the raw power of the machine.